everybody. I'll start again. Okay. Right. Good evening, everybody. Welcome to this second talk of 2024. It's a bit of a miserable night out, a bit of a miserable day altogether, I think. But hopefully we're all warm and cozy. It's my pleasure this evening to introduce Bob Holdsworth. Bob is Professor of Structural Geology, which simple title belies a rather significant academic career. Bob's geological journey started at the University of Leeds and Liverpool, but most of his career he's spent at Durham University, where his main research interests are, if he'll stand my précis, into faulting, fracturing and rock deformation. That can be corrected if it's wrong. And he's also worked in many areas of the globe, including Shetland. So he's aware of our local situation. Something for me stands out in his career, not a simple academic, if I can describe it that way, but much interest in the application of geological science, particularly in industries, including the oil industry and the nuclear industry. And particular significance to us, he is chair of the Scottish Geology Trust, and we join together with them in a mission to promote the wider enjoyment of earth science. If you read the whole of Bob's career in full, you might wonder where all the energy comes from, and we hope to find out this evening. Bob, please introduce your talk.
Very much for that. Hello, Shetland. It's always nice to talk to Shetland. I like Shetland a lot. I have to begin by apologising for the fact of my changing my talk at the last minute. I really was intending to do a talk on Fula, and I will come back at some future date and do that. But my problem is that I've just gone down to doing, I'm now on a 60% week. So I only work Tuesdays, Wednesdays and Thursdays, and it's fine. But I find that now I have to crush everything, instead of into 5 days, I have to crush it into 3 days, and I just couldn't do it in terms of other commitments. So I'm really sorry about that. But I had this talk sort of ready from a version of this that I did in Manchester a few months ago. And actually, you were mentioning there about the promotion of geosciences and geology to the wider world, if you like, and this talk is partly about that. And the clue to that, well, it'll become obvious why in a couple of slides' time, but it comes in the name Silent Witness, circa 1.2 billion years ago. So let's begin and try and explain what it is that I mean here, and why it is that I hope you're going to enjoy this talk, because it's actually one of the pieces of work that I did with students and colleagues that I probably, throughout my career, have enjoyed the most. Now, you're probably well aware that geosciences is in crisis. University enrolment in geology courses is falling very fast. It's falling even in places like Durham and Cambridge, which usually don't have a problem with recruiting geoscientists. Well, we certainly are now. And it is widely believed, as these articles shown on the right-hand side of the slide are talking about, that that's because geology has a bad press. It has a bad profile. It's thought to be associated with raping of the earth, with fossil fuel industries, and that really it isn't aligning at all well with current societal needs. It isn't aligning with the interests and desires of our younger generations. And it in particular has struggled to align with the UN Sustainable Development Goals, and those coloured squares there in the bottom right-hand side are a summary of those. I'm not going to go through them. But the basic argument in all of the articles there shown on that slide are that we need to repurpose the applied parts of geosciences to appeal to the expectations of future generations. And if we do that by emphasizing sustainable and renewable energy, careful use and reuse of resources, and so on and so forth, all will be good, and the young will come flocking back to the geosciences in great numbers. And that's all great, that's all good. But actually, to me, as a geologist, we're forgetting something here. And what we're forgetting is that the science of geology is actually a forensic science. And forensic science, as these selection of TV series indicate, has a huge and enduring appeal amongst the public. Silent Witness, which is a series that I actually dearly love, probably because I enjoy watching Amelia Fox, is the series that's just finished a couple of days ago. It was its 27th season. That's incredible. And you know, forensic science is something that captures the imagination of very large numbers of people, including young people. So this story, which is about a thing called the Clachtoll megaclas, is all about a forensic reconstruction. In this case, it's not a recent crime scene, it's something that happened 1.2 billion years ago, but it's something that was a catastrophe, and it requires a reconstruction in order to try and understand why it happened, and how we've deduced how it happened. And it represents a project that was funded by a local fund in Durham called the Charles Waite Scholarship. And the team of people who worked on it, and the person who actually got the funding in particular, was Zach Killingback. That's Zach there with the beard in the centre. He was the master's student who did this piece of work, supported ably by a variety of academics and other PhD students shown there on the on the right. This is me down here. My role in this was that the project was essentially based on an idea by. It was a bit like I was taking the Tony Warren approach to as he was the creator of Coronation Street, as you may know. But Zach is a student who still has special needs. He is quite severely Asperger's, but he wanted to do an advanced piece of research. He came through as an undergraduate and then went on to do this master's project. And he did an absolutely fantastic job. So good, in fact, that it led to the publication a couple of years ago of a paper in the high-profile Geological Society of America journal, Geology. So why am I presenting it to you up in Shetland? Well, I'm presenting it to you because, for me, this was a study that went right to the heart of why being a field-based geology is fulfilling and fun. And it's that aspect of the science that I think we need to try and convey and pass on to prospective students. Yeah, all the sustainable stuff is great, but we're forgetting geology is fun. Let's remember that. And actually, many children know that. But I'm also presenting it because it's testament to Zach and his willingness to overcome his difficulties and to take on what was, in fact, a quite complex, multifaceted problem. It's a study that also shows that you make mistakes, and in this case, it's me that made a mistake, and it's very important to admit to those mistakes. And finally, I think it's going to be interesting to you folk and everybody in general, because it raises some important philosophical issues around the science of geology and our view of processes back through geological time. Yeah. Let's explore that last point first. Geological time, of course, is vast. And of course, the person who played an absolutely pivotal role in understanding that was James Hutton. And he established what's sometimes referred to as uniformitarianism or gradualism. His famous statement being that the present is the key to the past. Everybody talks about that bit, but there's another bit: no vestige of a beginning, no prospect of an end. And wrapped up in Hutton's theory of the Earth is that the Earth changes slowly in uniform and cyclic ways. And that's why you can use the present to understand the past. And that's why there is no vestige of a beginning and no prospect of an end. But there was and is another way of looking at the passage of geological time. And this is called catastrophism. I never quite know how to say it, but anyway, which was created by Georges Cuvier, who was a Frenchman. And he had a very different view of the geological past. He said that the geological past, the geological record, is periodically interrupted by relatively short-lived destructive events, which he called catastrophes. And these can drastically reshape the Earth's surface or the flora and fauna. And this way of thinking about the Earth was largely based on his recognition of extinction events in the fossil record, because he was particularly interested. It's also been suggested that it was influenced by his very strong religious education, Catholic religious education. I'm not so sure that that's true. I think it really was the science that was leading him. And for a long time, these two different ways of looking at the Earth, gradualism or uniformitarianism versus catastrophism, were considered to be sort of opposing views of the Earth. Now, we now know, of course, that both of these sets of principles apply. Yes, the Earth does indeed change in slow, uniform and cyclic ways, but there are also, punctuating that history, a series on different scales of catastrophes. Now, our story here today, which concerns this area highlighted with the arrow here, basically, this is the community of Clachtoll, this is a little beach that lies just off to the side, concerns a very large fallen rock. And that was a large rockfall that occurred a long time ago, but it's an example of perhaps a relatively small scale catastrophic event. Now, big rocks that fall are known as megablocks, or I'm going to call them megaclasts throughout the rest of this talk. And it's the story of this big old fallen rock that I'm going to tell you, and how we reconstructed what happened forensically during that rockfall. And it's a story that has captured the imagination of many people, including National Geographic. As you can see here, this picture actually comes from National Geographic a couple of years ago. And this is their strapline for the story, and Zach's story, which they published in an article. And it's a very nice article. I recommend that you seek it out. Right, let's do a bit of geological background now. First of all, what do we mean by a megaclast? Well, a megaclast is a bloody great big rock, basically, or more specifically and scientifically, perhaps, it's a large displaced fragment of a pre-existing rock with a diameter greater than 1 meter. And we can then divide these megaclasts into a variety of blocks or megablocks and so on of different sizes. Megaclasts are observed on the surface in modern settings, but they can also occur in ancient settings, entrained within a sedimentary sequence. And the example I'm going to talk about is one of those latter ones, one that's entrained within a sedimentary sequence. They're found actually very widely on both the Earth and on other rocky planets. And there's a very nice example here of a megablock. I'm not even going to try and pronounce that crater, but it's a crater in the moon. And not only do you find the megaclast, which was blown out of the ground during a meteor impact many millions of billions of years ago, but you can also see its trace where it's bounced across the surface here. And you see there are some other ones here. Now, megaclasts form in a variety of ways, and this rather noddy little diagram is a sort of summary of the main ways. But the point about all of them is that they're all essentially catastrophic processes, short-lived, violent, and dramatic. But in the fastness of geological time, they occur in an instant, and they include things like volcanic and bolide impact-related megaclasts, like the one I just showed you on the moon, terrestrial mass wasting, rockfalls and landslides. That's the example that I'm going to be talking about today. Tsunami and storm-related features, and then things that happen in submarine settings, mass transport complexes, melanges, elytrostrams, and so on. But the thing to emphasize is that all of these are relatively short-lived catastrophic processes. And a relatively short-lived catastrophic process is, in the geological record, is actually a bit like a crime scene. Now, forensic crime scene reconstruction, the sort of thing that Amelia and her pals get up to, and indeed the real forensic scientists get up to, is the process of determining the sequence of events about what occurred during and after a crime. And that's essentially what we went through when we were trying to reconstruct what happened at Clachtoll 1.2 billion years ago. And as I've already said, we sometimes, just as they do in criminal investigations, we sometimes get things wrong and we have to revise some of our ideas. Right, let's talk about the regional geological setting then of this area. Right, we're up in northwest Scotland here. There's the little star indicating right along the coast. So this is Ullapool here. See now, before I make a terrible mistake and get myself wrong. So yeah, Ullapool is there, and the area where we're going to be is up here. This is Clachtoll up in this region here. We are therefore lying geologically to the west of the Moyne Thrust. Okay, so we're in the Caledonian Foreland, where we have Lewisian basement, a variety of Precambrian sedimentary sequences known collectively as the Torridonian sedimentary rocks, and then overlying them we have the Cambrian rocks, Cambrian Ordovician age rocks of the fallen sequence. Now, below the base Cambrian unconformity, shown in this cross-section, the rough location of that section, by the way, is just shown here, we have the Torridonian rocks, which are Mesoproterozoic sequences, which unconformably overlie the old Lewisian gneisses, the fundamental metamorphic basement of Laurentia. Now, the Torridonian rocks actually comprise two large, well, completely different in terms of their age, sedimentary sequences. There's an older sequence, which is relatively restricted in its occurrence, shown on this map in the sort of dark grey to black colour, which is known as the Stur group, which is dated at about 1.17 billion years old. And then unconformably sitting on top of that, you have the flat-lying rocks of the Torridon group, which is about 1 billion years old. And they're separated by an angular unconformity. And both the Torridon group and the Stur group sit unconformably on the underlying Lewisian basement. And the key thing about the Stur group is that it's associated with this fault, the Coigach fault, which is this big north-south trending structure labelled running essentially parallel to the northwest Scottish coast. Now, at the present day, as is shown in this cross-section, the Stur group dip at about 15 to 20 degrees to the west, and they're cut by the Coigach fault. And we know, for lots of reasons, that that fault was actually active at the time when these sediments were being deposited. We know that because there's lots of soft sediment deformation structures, lots of evidence of earthquakes and shaking during deposition of the sedimentary rocks. So that this is a classic example of what we call a syn rift sequence, something that was produced by continental rifting and deposition of these sedimentary structures in some sort of half-graben setting. Now, this is a sort of fairly schematic sedimentary log through the entire Stur group succession. So I'm going to forget about the rest of the Torridonian now. We're just going to focus on the Stur group. And more specifically than that, we're going to focus on the lower part of this sequence. But the overall sequence that you have here is red beds, they're alluvial, fluvial, and lacustrine continental sequence. As I said, they were deposited about 1.2 billion years ago. That's based on the age of some cave feldspar cements that are associated with this unit, this very famous unit known as the Stackfada member, which is an impactite. That's to say a deposit that's believed to be associated with a meteorite impact at the time when it was deposited. But the rocks we're actually going to be concerned with occur right down at the base of the Stur group in the lower Clachtoll formation, and they're the ones right at the bottom, these basal breccia conglomerates, which are basically conglomerates made up of lumps of the underlying Lewisian gneiss with a red sandstone matrix. And they were deposited in sort of canyon paleotopography. Okay, so here's one of these paleo valleys, a little paleo valley filled with this breccia conglomerate, eroded into the underlying Lewisian gneiss. And that's the basal unconformity of the Clachtoll formation. And in fact, you can map it out right across the Stur Peninsula here. And it's this very irregular boundary that I'm running the pointer along here. And these bits that stick out here, 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 and down here where we are, these are paleo valleys. Now, those paleo valleys are cut into the underlying Lewisian gneisses. What about them? Well, the Lewisian gneisses are Neo-Archean. They're about 2.8 billion years old. They comprise banded gneisses, sort of typically acid, intermediate, mafic orthogneisses. That's to say, igneous rocks originally that have been metamorphosed up to amphibolite facies. They contain a very famous set of west-northwest, east-southeast trending basic dikes known as the Scourie dikes, which are about 2.4 billion years old. And they have in this area a very steep east-southeast, west-northwest foliation, which is related to a large-scale structure down here called the Canisp shear zone. So this is the northern margin of that shear zone, and most of the fabrics here are running west-northwest to east-southeast. And there is that fabric. That's the fabric you can see in the hillside underneath these Stour group rocks. And that kind of shear zone, which is a dextral shear zone, is a strike-slip dextral shear zone, is about between 2.4 and 1.6 billion years old. Now, where we're going is here, just at the south end of the Clachtoll area. What do we have here? Well, the traditional wisdom for this particular area involves a thing called the Clachtoll fault, which was identified in a paper by Beacom et al., of which I am one of the authors. And one of the things that we noticed in this area was that there were a whole series of fractures and veins that are filled with red sedimentary material. Red sedimentary material that looks very similar to the sediments of the Stour group, which lie very close to it. In fact, this is all Stour group sediment just over here, close to these rocks. And we argued that the development of these sediment-filled veins and fractures was associated with the development of this Clachtoll fault. At that time, Beacom et al. Recognized that some of the sediment fills were laminated and appeared to be open fractures that had infilled by basically sediment being washed in from above, whilst others, like these ones here, were clearly injected. And this seemed to be related to remobilization and overpressuring of unconsolidated sediment. And so what we did was we said, well, it's related to this fault zone, which you can see exposed on the shoreline, which we called the Clachtoll fault. This fault was moving, it was generating overpressure, pumping fluids around, and that's what caused the injection of these veins. And what we then said was that, well, that fault, the Clachtoll fault, is related ultimately to the Koigath fault, so it's all related to the regional rifting and earthquakes and shaking that was going on during the development of the Stour Group Basin. All seems to make sense. However, it's completely wrong. There are a number of problems. Here's a detailed map of that area where you find most of the veins. And this brings us, and sediment-filled fractures, and this brings us actually to the first point, which is that the sediment-filled veins and fractures are largely restricted to this area of Lewisian rocks. Okay, these red things on here basically are meant to represent those veins and fractures. And that area of Lewisian is completely identical to the adjacent Lewisian in terms of its lithology, but it's completely different because the foliation is almost at 90 degrees. This is the foliation traces in the main part of the Lewisian, and this is the foliation in this area, and you can see it's almost at 90 degrees. So it's very strongly misoriented. The other problem is that this is the only place where you find these sediment-filled fractures and veins. There are virtually none in the Lewisian over here, only here. The other problem is that the Clachtoll fault, which dips at about 45 degrees to the northwest, it's basically a left lateral thrust. It has a displacement of about 3 meters because we can see this off unit of mafic Lewisian is this unit here, so it's got about a 3 meter displacement. It cuts this area of misoriented gneiss. Here it is. This is it actually on the map, but it's tiny, and it doesn't run into this big gully, which is what Beacom et al. Had inferred. It doesn't, so you can't run a fault all the way through here to explain the misorientation between this piece of Lewisian and this piece of Lewisian. This is just a little structure. It's tiny. So the Clachtoll fault, as envisaged by Beacom et al., including me, does not exist as a large-scale structure. Right. Let's look again then at our crime scene. All right, here's that geological map that I showed before. This is a view essentially taken from the south end of this map, looking kind of to the north-northwest. Okay, let's just identify what the key components are. Well, over here, we've got in the foreground, we've got the Lewisian with the sort of northwest-southeast trending foliation, no sediment-filled veins or fractures. Over here, forming this hump, this very distinct hump-like hill, we have the area of misoriented Lewisian, which has many sediment-filled veins associated with it. We've got a gully, a modern gully that separates the two, which corresponds to this area here. We've got the basal breccias of the Stour group here, and there's the basal unconformity between the Lewisian and the Stour group, runs down there, goes over there, and in fact, it actually sits on top of this misoriented area over here as well. And then higher up in the Stour group sequence, this is the basal breccia. Higher up, we have the rest of the west-northwest dipping Stour group, dipping at about 25 degrees to the west-northwest. And then Clachtoll fault is just there. Okay, in fact, it dies out just not very far from this point. So it really is a very small structure. And it certainly isn't any feature that you would recognize in this modern gully. Right. Now, in order to understand what's going on, what we started to do is we said, all right, well, let's look again at the contact relationships. And let's start with something that we're absolutely certain about, first of all. Let's start with the relationship between the basal breccias of the Stour group and the underlying Lewisian. Okay, and what we can see, it's very, very clearly an unconformable relationship. These massive sheet-like breccias sitting on top of the Lewisian with this strong northwest-southeast foliation within it. And this is clearly some sort of paleo valley, dipping actually quite steeply to the west-northwest. Okay, with all the clasts of material in this breccia being derived from the local Lewisian basement. So they haven't come very far at all. Okay, so if we go over here to this side of the misoriented area, we actually see more or less the same thing. We see this basal part of the Stour group onlapping onto the unconformity surface with this misoriented Lewisian below. And on the top here of the mound, we actually find little veneers, thin veneers of breccia onlapping onto the or sitting on top of the Lewisian, representing the sedimentary material that originally covered over these rocks. But of course, the difference, so the contact relationship is in fact exactly the same as what we see over here. The difference, of course, is that here the foliation in the Lewisian is going northeast southwest, whereas over here it's going in almost at 90 degrees to that. All right, well, let's get into the detail, because what really matters is what's going on in this modern gully. Now, for many years, this modern gully was full of great big boulders, and it still is to some extent. Here's one of them just here, and there's a whole series of other big boulders. But recent storms, 5 years ago, cleared out this gully, and they exposed some critical relationships. In particular, this area here, 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 and here is not loose blocks, it's actually in place. And what we see here is basal breccia of the Stour group sitting unconformably on top of the Lewisian, the main Lewisian that lies to the east over here. But what's clear is that the area of misoriented Lewisian here is sitting on top of those breccias. Okay, so this area here is actually sitting on top of the Stour group rocks that crop out on either side of it. And there's the modern gully, and there's no fault as such in there. It's just a gully. So this led to the idea, this was the idea that I had at the beginning of Zach's study, that what we were looking at here is that this is a big misoriented area which represents a large megaclast. And Zach set about mapping it, as you can see here, this is his geological map, in beautiful detail. And one of the things he did once he'd mapped out the boundaries was to draw stratum contours along this contact, which is in fact the basal contact of the clast. And what he showed, we look at this section here, from B to B prime, so that's from there to there, is in fact that the base of the clast is dipping really quite shallowly. It dips at about 10 to 25 degrees. And that means that this clast, although it forms that sort of lump, that mound, it's actually at its maximum extent only about 15 meters thick. So it's 100 meters long, 60 meters wide, and 15 meters thick. That means that if this is a clast, it has a volume of about 90,000 cubic meters, And if you take a representative density of the Lewisian gneiss of about 2.73 grams per centimeter cubed, that means it weighs about 250 kilotons. So you wouldn't want that landing on top of you. Now, what about the sediment-filled fractures and veins? Well, Beeker et al. Were quite right about there being two different types. There are indeed laminated sediment fills, okay, which have bedding in them. Here are some of those examples, beautiful laminations, you get pebble imbrication and so on. These are red sandstone matrix breccia conglomerates. They are locally developed in fissures or fractures, open fractures that are parallel to the foliation, and in other places they cross-cut. It varies. The laminations, interestingly, if you plot them on a stereonet, the laminations in the sediment-filled fractures here are shown in red. The Stur group bedding in the overlying Stur group is shown in black, and you can see they coincide. So the bedding here in these sediment-filled fractures is parallel to the dip of the bedding in the overlying Stur group. And it's pretty clear that these were open fractures on the basement into which material was washed by sediments, and sometimes they show this beautiful curved geometry, which is known as a catenary lamination. And this is thought to form by basically sediment being washed into enclosed spaces and sticking to the side of the fracture. So you end up with this concave up bedding form. Catenary, by the way, comes from chains, which show catenary patterns when you hang them like this. It may also be because there was a little bit of compression. I'll come back to that later anyway. They're sediment fills. They represent material that's been washed in from above into open fractures. But many of the other sediment-filled fractures are very different. They're massive. They contain no bedding whatsoever. They're chaotic. They are filled with a much finer grained, homogeneous red sandstone, which often contains matrix-supported clasts of the host gneiss. Many of these show upward, they die out upwards as you look up into the cliffs of the misoriented basement. And they have this often jigsaw brecciation, where you can see the rocks being broken apart. And these sorts of features are consistent with this material being mobilized sediment that's been injected at high pressure into the basement rock and blown it apart. And in some cases, you actually see alignments of the fractures, of the clasts rather, parallel to the fracture walls. So these are injection features. There's absolutely no doubt about that. And again, Beeker et al. Were correct about that. But what they didn't spot was that these different types of sediment-filled fractures have distinct distributions. Specifically, the central and upper part of the misoriented area, our putative megaclas, is where the laminated sediment-filled fissures and veins, fissures and veneers occur, whilst the injected veins are particularly well developed, basically all around the sides and towards the base. And what's more, the injected ones particularly show a fairly strong northwest-southeast alignment. There's a predominance of northwest-southeast strikes and subvertical dips, which kind of sort of suggests that there's a northeast-southwest extension going on here during the both the opening up of the fractures that are filled with laminated sediment and the injected fractures. So we thought, okay, let's come up with a working hypothesis, just like they do in crime scene restoration. We said, well, let's envisage that this was a large block of gneiss, okay, and that it fell onto very recently deposited, still essentially unconsolidated breccia conglomerate below, which was still full of water. As it landed, because it was, remember, 250 kilotons, it caused a catastrophic but highly localized overpressuring in the underlying fluid-laden sandstone matrix. That led to hydrofracturing, an injection of mobilized sedimentary material into the base of the megaclast, okay, both along the base and round the sides. And also, because of the shock of the impact, you opened up a whole series of open fissures and fractures on the upper exposed surface of our fallen block. And then that block was then buried by continuing sedimentation. So there was a later phase of sediment filling, which was gentle and was associated with the development of the laminated fills. So a sort of corollary of this is that the laminated fills are actually slightly younger than the injected fills. Now, if this is a proper piece of forensic science, though, we need to test these ideas scientifically. And the two questions that we wanted to ask was, well, how far did this block actually fall? And I think I maybe should have said, are the injection processes here mechanically feasible? Well, first of all, what caused it to fall? Why do large clasts like this fall in any case? Well, clearly the megaclast is of local basement origin. So if it fell off a nearby paleo cliff. The likely triggers for that? Well, the most obvious one is seismic shaking, because there was a lot of seismicity associated with the deposition of the stir group in general, which was consistent with its sin rift setting. Or it could be because of freeze-thaw action, which is the repeated freezing and thawing of groundwater, which leads to the expansion and contraction of ice to water to ice to water, which eventually levers off your block and causes it to fall. And some people have suggested that the stir group was affected by periglacial environment. One thing that we can be sure of, however, is that this catastrophic collapse event is not related to the Stackfader impact event. And we can say that with some certainty because the Stackfader impactite is 500 meters higher up in the sedimentary sequence. So the megaclast had clearly fallen into place and been buried by the basal Clachtoll formation sediments long before the meteorite impacted with the region to the west, probably of northwest Scotland, to create this impactite. So whilst it's very tempting to say, oh, the fall of a big block, it's bound to be due to a meteorite, I think that's extremely unlikely because basically the meteorite didn't happen for many thousands or even millions of years later. Okay, so let's get a little bit scientific now and let's ask the question, well, okay, how far did our megaclast fall? Well, in order to answer that question, we have to make a whole load of assumptions. We have to assume that it's a simple vertical displacement, it's a vertical fall of the megaclast. We had to make assumptions and say, well, we're going to assume initially that it's homogeneous, that it's an elastic material, and that it landed with a flat base onto whatever was underneath. So it was a flat impact. So all of the underlying surface is impacted at the same time. We started out by considering it as a solid against solid collision, but then went on to consider it as a solid against water impact. But the idea was that by splatting our rock down onto water underneath, this would lead to a transient overpressure in the underlying fluid, water, which corresponds to our water-laden sediment, whilst the corresponding stresses that would be generated in the overlying block would also help to split it apart. This is some of the key equations that we played with. I'm not going to take you through them, don't worry, but just to show that there is a bit of hard science underlying this. But before we can show you the results, we had to actually find out some more information about the Lewisian basement. We needed to know what its tensile strength is. And in order to work out tensile strengths, you do a thing in the lab called a Brazilian test, which is basically where you put a cylinder of Lewisian gneiss between a simple loading cell with these jaws to crush it together. It's a bit like crushing something in a benchtop press. And basically you keep crushing them until they split open. And I've got a nice, at least I thought I had here. Hold on. I'm not going to be able to play that. Oh, there we go. Here's a movie taken. What happens? Slowed down. So this was done using a high-speed camera. You can see the tensile fractures there cracking, and the point at which it cracks gives you the tensile strength. And we did a whole series of experiments with the pre-existing foliation in the Lewisian gneisses in different orientations. But actually that didn't make a huge amount of difference. And what we discovered from those experiments that the range of tensile strengths for Lewisian rocks is typically between 6 and 12 megapascals, which is, it seems like a sensible number. What we then did was we were going to assume that was hydrofracture occurred when the pressure surge, that was produced by the impact was greater than the cumulative value of the tensile strength, and the transient stresses that were generated. So that generates an impact velocity, And then we applied a thing called the free fall equation, and that gave us the minimum height of the block fall that was required. And we then sort of explored a range of different parameters compatible with Lewisian gneiss and fluid-laid sediment. That's what all that table's about. Okay, so here are the range of tensile strengths. These are all these other parameters, but here are the critical figures. These are the impact velocities, and these are the heights of fall. And what you can see is that our analysis suggests that the impact velocities were probably somewhere between 7 and 15 meters per second, and that the fall height that was needed to cause this was somewhere between about 2.5 and 11.2 meters. Let's say less than 15 meters. Now, given that the basal Clachtoll formation has a paleotopography associated with it, the paleovalleys, which show a local relief of up to 150 meters, the fall of a large block, less than 15 meters from a cliff, is entirely geologically reasonable. So what we've done in this rather arcane mathematical analysis is we've shown that our hypothesis is mechanically reasonable and geologically reasonable. And that is, if you like, the fundamental tenet of much of forensic science. But of course, it wasn't just a simple vertical fall. What else happened? Well, we know, for example, first of all, that the clast has rotated at least 90 degrees about a relatively steep subvertical axis. We also know that the base of the clast dips between 10 and 25 degrees to the southwest. And that's quite important because if the clast is actually lying on a slope, then it's quite likely to experience some internal deformation in the same way that landslides experienced internal deformation. And if this is southwest is to this side over here, we would expect then the front of this thing, the thing at the base of the slope, to perhaps experience compression, and the back and central part of our block here to experience extension in the same way that landslips and landslides do. And guess what? The compressional features that we find, including the original Clachtoll fault, which is associated with this rather chaotic fold and breaking apart and injection of sediment, is a shortening feature, and it occurs at the front of our block. Whilst the middle and back of the block are full of extensional fractures, which, if you remember from our earlier analysis, predominantly trend northwest, southeast. And that is consistent with extension at the rear and in the center of our block as it slid down the hill. It's also possible that the catenary bedding lamination was caused by initially opening fractures and then shortening them a bit as the block came to a halt as it slid down the slope. So let's take all of our evidence now and finally reconstruct the catastrophe. Well, what we think was initially we had our 250 kiloton megaclast pivoting off a cliff and falling less than 15 meters onto recently deposited, still thoroughly wet breccia conglomerate below, and maybe some water as well. That then caused catastrophic local overpressure and mobilization of the fluid fluid-laden sediment, particularly the sandstone matrix, leading to hydrofracture and upward injection of this material into the overlying block. Whilst still nicely lubricated on that cushion of overpressured fluid, it then began to slide down towards the southwest, possibly rotating as it goes in order to produce the required rotation. And then as it begins to slide, and as it slides and comes to a halt, it undergoes internal deformation with tensile fracturing in the back and in the middle part of the block, and thrust faulting and folding in the frontal part of the block as it comes to a halt. And then finally, it stops and it's buried gently beneath further sedimentary fills, and those open fractures that formed when the block landed are gradually filled with sedimentary material, okay, to produce those laminated fills. So there's the overall sequence of events, 1 to 5. There's our reconstruction of our catastrophe. And the key thing to remember here is, although this is 1.2 billion years ago, stages 1 to 4 in that sequence probably occurred in no more than a few minutes, possibly even just a few tens of seconds, which is, gives me pause for thought anyway. So I hope I've convinced you that this is a plausible forensic reconstruction of an ancient catastrophe, and it shows us a number of really quite important things. I've shown you that the 250 kiloton fallen megaclass model is consistent with the evidence and with the local sin depositional topography and the tectonically active setting of the Stur group and its proximity to the Koigach fault. A model with a less than 15 meters vertical drop has been shown to be physically and mechanically possible and plausible. It's a catastrophe that's not related to the much bigger Stackfader impact event, because the megaclass lies much lower down in the stratigraphic sequence and clearly deformed demonstrably earlier. And perhaps more generally, our findings show that megaclasts like this exist in the terrestrial geological record as far back as the Mesoproterozoic. And in fact, at 1.2 billion years, this is at the moment the world's oldest documented terrestrial megaclast. But my final slide, I want to say this. I want to return to the theme that I started with. The present is the key to the past, and geological science is a forensic science. Okay, it's the application of scientific principles and methods to reconstruct and better understand sequences of events that occurred in the past. It's absolutely central to what we do as geologists, and to me, it's why geology is so much fun, and it's that we need to convey to our young people. Because the message here is that the present and the past are finally and ultimately going to be the keys to our collective future. Thank you very much. I'll unshare, I guess, if I can remember how to.
And I'll stop recording now.
Let me see.